Hello, chemistry students. Today we're going to talk about the heat of solution and heating and cooling curves. So, as a reminder from first semester, we were talking about the dissolution of a solute into a solvent. And when that happens, your solute has to separate and break those IMF forces. And in order to do that, you have to add energy. And in your solvent, you have to separate the solvent particles, the IMFs between those, and add energy. And then when those two come together, your solute and your solvent, they mix and they form new IMFs, and you make a solution. So you can think of this as breaking bonds, or IMFs, and you can think of this as forming new bonds, or IMFs. So the attractions in the solute, are they breaking or forming right here? So here they're close together, and here they're far apart. So that would mean that you are breaking the IMFs. Now if you're breaking bonds, you should think takes to break, and that takes energy to break. So if it's going to take energy, it's going to be endothermic. Would the change in enthalpy for this step, delta H sub 1, right here, this step right here, be positive or negative? If you're adding energy, then it will be a positive, delta H. So now let's look about step 2. So again, we're going to answer the same questions, only now we're going to talk about the solvent here. So for delta H sub 2, or step 2, we have to expand the solvent, so we need to break these IMFs right here to go from close together to further apart. So you are breaking attractions. All right, so if you're breaking the attractions, the process will be endothermic because it takes to break. The change in enthalpy for this would be a positive change because you have to add heat in order to break those attractions. You have to add energy. So let's go back up here. Your delta H here will be positive because you have to add energy in order to break those IMFs. And over here it would be positive because you have to add energy in order to break IMFs. So now let's focus on step 3. So we're going from two separate things, your solute and your solvent, and we're going to mix them. So are IMFs in the solution breaking or forming? If they're mixing, you're forming new IMFs right here. Okay, you're forming new IMFs here. If it takes to break, it frees to form. And that's frees energy to form IMFs. If it frees energy, that means you're releasing energy, so it will be exothermic. If it's exothermic, that means it's releasing heat, so your delta H will be negative. So if we look up here, our delta H will be a negative value. So the overall delta H for forming the solution would be the sum of all of the steps above, your delta H sub 1, delta H sub 2, and your delta H sub 3. Keep in mind that the strengths of the attractions, in other words, the lattice energy for ionic compounds, the IMFs for covalence, would impact the amount of these heat values. If you remember correctly, last semester, ionic compounds take more energy to break than intermolecular forces. If the energy absorbed in steps 1 and 2 combine to be larger than the energy released in step 3, would the overall process be endothermic or exothermic? So let's think about this. So we've got step 1 and step 2. and these are positive values. And it says if this is larger than step 3, or the energy released in step 3, which is a negative value, you're going to have a positive value. Therefore, your process will be endothermic, because if your delta H is positive, you need to add heat. If it's endothermic, that means the reaction is taking in heat, so the solution will get cold because it is removing heat from the surroundings. If the energy absorbed in steps 1 and 2, so let's do this again. Step 1, it's a positive value. And step 2, this is an endothermic reaction right here, or endothermic process. If that is smaller than or less than step 3, which is an exothermic process, if this number is larger than these two added together, you'll have a negative delta H. A negative delta H indicates that the solution or the reaction is exothermic. If it's exothermic, it's releasing heat. If it's releasing heat, your solution would be hot. So we need to answer the following questions about the dissolving process of sodium hydroxide in water. We know that sodium hydroxide is a strong base, so it will completely dissociate in water. What kind of attractions would be broken in sodium hydroxide when dissolving? So we have to think about what type of compound sodium hydroxide is. Sodium hydroxide, hopefully you remember, is an ionic compound. So ionic bonds will be breaking. What kind of attractions would be broken within water when dissolving? So we have some water molecules. Okay, this is a covalent compound, and it's a polar covalent. There's a partial negative here and a partial positive on your hydrogens. So the kind of attractions that would be broken here are your intermolecular forces. You've got a positive, partial positive here on this hydrogen and a partial negative on this hydrogen. So the bond or the attractions that are going to be broken are right here, which is a hydrogen bond. Okay, covalent compounds have other IMFs. This happens to have a dipole, so these are dipole bonds. Or dipole-dipole. And everything has London dispersion, so you also have to break your London dispersion intermolecular forces. What kind of new attractions would be formed between the sodium hydroxide and water? So now we need to think about once sodium hydroxide dissolves in water, you've got your sodium ion, you have your hydroxide ion, you have your polar water molecule, which is a partial negative on the oxygen, and your hydrogen is partial positive. So you have this IMF right here between your sodium and your oxygen, and you have this IMF right here between your hydrogen and your hydroxide ion. This IMF is an ion dipole. This IMF right here is also an ion dipole. Everything has London dispersion, but that is much weaker. But that is also another force of attraction that is being formed. Okay, let's look at letter D. It says write a dissolving equation for the dissolution of sodium hydroxide. So we have sodium hydroxide. It is a solid, and it's talking about it dissolving. Usually we write H2O on top of your arrow because we don't want to put water on the reactant side and water on the product side because it ends up canceling out. So we usually denote a dissolving process with water on top of an arrow. And once this dissolves in water, it separates into its sodium ion, and it's aqueous. It is aqueous. Plus your hydroxide ion, it too is aqueous. Don't forget to put the states. Okay, it says when 1.095 grams of sodium hydroxide is dissolved in 150 grams of water at 23.5 degrees C in a coffee cup calorimeter, the final temperature is found to be 25.32 degrees C. Calculate the heat change when sodium hydroxide dissolves in water. We're going to assume that the specific heat of the solution is approximately the same as that of water, and no heat is absorbed by the calorimeter. All right, so we're looking for heat change. So we're basically looking for Q, or delta H. And we know that that is equal to MC delta T. All right, but if we notice here, we are given the mass of sodium hydroxide, we're given the mass of water, we're given two temperatures, the solution or the water, and we're given the specific heat of water. So likely what we're going to have to do here is calculate the delta H of our water. Now, when we dissolve things, there's a warning here that I'd like for you to look at, because normally we do the heat lost by one thing is equal to the heat gained by the other thing. Or in other words, the heat lost by water is equal to the heat gained by your system, or the heat lost by your system is equal to the heat gained by your water. But this is a little bit different when we're dissolving because our system is actually inside of our water. So when we dissolve solutions, we add the mass of the water and the ionic compound together in our MC delta T formula. This is because both substances are contributing to the total solution, and that's what we are measuring. We're measuring the solution temperature. All right, so what we're going to do here is we're going to add our mass of our sodium hydroxide and our mass of our water, delta H calculation. So delta H is going to equal 151.095 grams. And we're going to multiply that by C, which is 4.18 joules per gram degree C.
Come over here.
Times your delta T. The delta T is the final minus initial. Now it says here that our final temperature is 25.32 grams. Our initial temperature is 23.50. And that's degrees C. We're going to cancel our units. We have a gram in the numerator, a gram in the denominator, so they cancel. A degree C in the denominator and a degree C in the numerator, so they cancel. If we calculate all of this out, our delta H, which is 1,150 joules. Our answer should have 4 sig figs, which is why I put the decimal here, because our temperatures each have 4 sig figs and our masses each have 4 sig figs. Now let's think about this. We need to check and make sure our signs are okay. It says here that our solution gained 1,150 joules of heat. So if it gained heat, then that would mean that the temperature decreased. Shows here that we started out with 23.5 degrees C and it went to 25.32 degrees C. So our water actually heated up. If our water heated up, then that means that our solution had to release heat, okay, to go into the water. But here it shows that our delta H is positive. We know that the delta H of our reaction could not have gained heat, because if it did, then the temperature of our water would have gotten colder. All right, so the process of dissolving sodium hydroxide is an exothermic reaction. I know that because our temperature increased. It went from 23.5 to 25, so it has to be an exothermic process, which means the delta H for our dissolution process must be negative. So we're going to put a negative sign in front. Was the dissolving process endothermic or exothermic? It's exothermic because the temperature of the water increased. If the temperature of the water increased, that means that it would feel warm or hot to the touch. It's an exothermic process. Calculate the heat of solution in terms of kilojoules per mole of the NaOH. So we know that negative 1,150 joules of heat was released for 1.095 grams of NaOH. And we need to find out how much it was per mole of NaOH. So we can do some dimensional analysis to convert this. We know that, again, that 1,150 joules of heat was released for every 1.095 grams of NaOH. All right, we need to convert this joules to kilojoules. There are 1,000 joules in 1 kilojoule. Therefore my joules will cancel and I'll be in kilojoules per gram, but I need to be in kilojoules per mole, so I need to convert my grams to moles. This is molar mass, and the molar mass of sodium hydroxide is 40 grams in 1 mole. I have a gram in the denominator and a gram in the numerator, and they cancel. So the heat of my solution will equal a negative 42 kilojoules per mole. Okay, now let's talk about heating and cooling curves and the calculations that we need to do from those. So a heating and cooling curve shows what happens to the temperature of a substance as heat is applied or removed, and the transitions between the different states, solid, liquids, and gases. So remember, there are no temperature changes during a phase change. If you notice here on the graph, during phase changes of melting and vaporization or boiling, the temperature does not change, even when you're adding heat. Okay, so if we're moving across the graph from left to right, in other words, we're heating it, all of the energy, the heat energy that's absorbed when a phase change is occurring, is used to break the IMFs, not to increase the kinetic energy. We know that because the temperature is not increasing. Temperature is a measure of average kinetic energy. So we're changing the potential energy, not the kinetic energy during phase changes. If it helps you to remember, or use the 3 P's of the heating curves to remember this. All right, plateaus on a graph. Equal the phase changes, which equals potential energy changes. So the 3 P's. All right, calculations using our heating and cooling curve is basically a modification of our Hess's law. You know, when we have our 2 or more equations and we have our delta H's and we rearrange those equations to get our final one, and we add up our delta H's together, that's kind of like Hess's law. So the total enthalpy change for a process is going to equal the sum of each individual step. So if we're moving across the curve from left to right, in other words, we're heating them, the process is endothermic, we're adding heat, and your delta H for the process going in this direction will always be positive. If you're moving down the curve, if you want to call this a curve, or from right to left, the process is exothermic because we are cooling, so it has to release heat. The delta H for the process will be negative. So there are several steps to this calculation. Okay, so if you are not given a heating and cooling curve, sketch it out. Indicate your melting and boiling points at the plateaus of the graph when you do that, because those are separate calculations. Mark on the graph which sections are being discussed in the problem. That way you don't forget any steps. It's a common mistake to forget a step like a plateau or a phase change. You're going to complete a calculation for each segment. We're going to use delta H equals MC delta T for segments that involve temperature changes. In other words, when you're heating or cooling a solid, heating or cooling a liquid, or heating or cooling a gas. So those are the diagonal portions on your heating and cooling curve. This formula will come out automatically with the correct sign when you do your delta T final minus initial. Make sure you are addressing the heat change of the segment only, not necessarily the total temperature change. I'll go into an example of that in just a moment. You're going to use the heat of fusion and heat of vaporization for segments that involve phase changes or your plateaus. So your heat of fusion is when a solid goes to a liquid, or when a liquid goes to a solid. Use the same heat of fusion calculation. You just change the signs. You use your heat of vaporization for when a liquid goes to a gas or when a gas goes to a liquid. You're just going to change the sign depending on if the process is going to require a loss of heat or a gain of heat. In other words, whether or not you're boiling or vaporization, you're going from a liquid to a gas, or that would be a positive because you have to add energy to do that, or if you're going from a gas to a liquid or you're condensing it, that will release heat. These values typically tell us the heat change associated with changing the phase per mole of a substance. On occasion, the value can be given in grams instead of moles, so make sure you put your units and you cancel them out, okay? Because if you don't, you could mess that up. Next step is you're going to add the heat values for the segments you calculated. You just add them all up. All of the sections have to have the same sign because you're usually going in one direction. You're not going back and forth. All sections need to be in the same unit. You will have to do a conversion because likely the phase changes are given in kilojoules and your diagonal changes or your heating and or cooling of a phase is usually given in joules. So let's do an example. So we have a heating curve for methane. So what is the melting point of methane? So we're going to look at this, all right? This first diagonal usually indicates or a solid, all right? So this is going to be our solid. So our melting point is going to be right here because R is our liquid. Our melting point is 90 Kelvin. You can usually tell this that it's melting also by heat of fusion. This is basically when a liquid fuses into a solid. They call it heat of fusion. What is the boiling point of methane? That's where your delta H sub vaporization is. And that's this part right here, S. So the boiling point would be 110 Kelvin. This would be section Q, and this is section S. Which segments would involve changes in kinetic energy? Temperature is the change in average kinetic energy, or is a measure of average kinetic energy. So anything where the temperature is changing is where your kinetic energy is changing. So that is in section P, section R, and section T. Because the temperature is not changing in section Q, nor is it changing in section S. In letter D, it says which segments would involve changes in potential energy. Potential energy is when you're adding heat and the kinetic energy is not changing. Just potential energy is. So when we're adding heat, we're going to look for areas where the temperature doesn't change. And that is section Q and section S. So now we're going to answer E. It says, in which segment would the intermolecular forces be the strongest? So on this, you're going to have to think about what the intermolecular forces do. And they keep a solid, they keep a liquid, and once all the IMFs have been broken, liquid will turn into a gas. So your gases have the weakest IMFs, and your solids have the strongest because they move very little compared to a liquid and especially compared to a gas. So the segment that where the IMFs would be the strongest would be the solid segment, which would be P. The segment where the IMFs, or the intermolecular forces between the methane molecules, would be the weakest would be in the gas phase because they have very little attractions to each other because they're far apart, and that would be section T. In which segment would there be the most molecular movement? That again would be section T because you're in the gas phase and they're moving quickly or much faster than in the liquid and or the solid phase. Okay, let's look at H. It says, why might segment Q be shorter than segment S? So let's look at this. Why is Q shorter than segment S? In other words, it doesn't take much energy. You don't have to add much heat energy in segment Q as you have to add in segment S. So let's think about IMFs here. In segment Q, your IMFs are just loosening or weakening. It's going from a solid to a liquid, so they're not completely broken. In segment S, your IMFs completely break because you're going from a liquid to a gas. Your IMFs completely break. This needs quite a bit more energy. Think Coulomb's law. In order to do that, you have to add more energy in order to separate the molecules in a far enough distance, have no longer an attraction to each other. Letter I, it says methanol has a heat of vaporization of 38.3 kilojoules per mole, which is significantly higher than methane's heat of vaporization of 8.2 kilojoules per mole. Why might this be the case? Again, we need to think about IMFs. Methane, or CH4, only has London dispersion forces. Methanol or CH3OH also has London dispersion, but it also has hydrogen bonding because you have, and these are strong, stronger than London dispersion, so it needs more energy to break them. Which segments would use the delta H is equal to MC delta T in order to calculate the enthalpy changes? So basically on here you have to have a change in temperature in order to use this formula. So any segment that is changing in temperature, which are segments P, segment R, and T. Determine the amount of heat needed to change 5 grams of methane gas from 120 Kelvin to a liquid at 110 Kelvin. The specific heat of methane gas is 2.22 joules per gram per Kelvin. So the first thing we're going to do, if we don't already have a heating cooling curve, we'd sketch it. We already have a heating cooling curve, so we're not going to do that. Second thing we're going to do is we're going to label our changes on there. Okay, so the first thing we're doing is we're going from 120 Kelvin to 110 Kelvin. All right, and I'm going to look up here. 120 Kelvin is right here. All right, so it is a gas, and it's going to 110 Kelvin, which is right here. All right, so this is going to be step 1. But it also says that it needs to go to a liquid. All right, so it's going from a gas to a liquid. At this point right here, it is still a gas at 110 Kelvin. So we need to go to a liquid at 110 Kelvin. So right here would be step 2. So step 1 right here will involve a temperature change, so we can use MC delta T. And step 2 right here does not involve a temperature change, so we're going to have to use the heat of vaporization to calculate that. we've got the gas and it's going from 120 Kelvin. So this is our initial temperature. And its final temperature is 110 Kelvin. It's going from a gas to a liquid, which means we need to do a phase change. Okay, so step one, we have determined that we are going to use MC delta T because we are cooling a gas. So our delta H, and I'm going to put sub 1 for step 1, is going to be MC delta T. So the delta H for step 1 will be the mass of methane, which is 5 grams, times the specific heat of methane, which is 2.22 joules per gram Kelvin, times the change in temperature, which is final temperature is 110, minus initial temperature, which is 120, and those units are in Kelvin. I'm going to cancel out my units here. I have a gram in the numerator and a gram in the denominator, so it cancels. A Kelvin in the numerator, Kelvin in the denominator, so it cancels. And my delta H sub 1 for step 1, if I multiply and divide all of this, is going to equal negative 111 joules. All right, so we're going to keep this. This is step 1. Now we have a gas at 110 Kelvin, but we need to turn it into a liquid. So step 2, we are going to condense our gas to a liquid. In order to do that, we're going to have to use our heat of vaporization. The delta H of vaporization is equal to 8.2 kilojoules per mole. And we need to calculate that out for 5 grams. Also, this is in kilojoules, and my delta H sub 1 for step 1 is in joules. So I'm going to go ahead right now and convert this to joules. And I'm also going to convert my moles to grams, all right, to find out how much heat I was given. All right, so the delta H for this for step 2 will be 8.2 kilojoules of heat for every 1 mole of methane. But I need to put that in joules of heat. So there are 1,000 joules for every 1 kilojoule. My kilojoules will cancel. I am now left with joules per mole. I know I have 5 grams, but my 5 grams isn't going to work with this mole. All right, so I need to get rid of my mole, and I need to convert to grams. All right, so for every 1 mole, I'm going to do the molar mass of methane because it's grams per mole, and the molar mass of methane is 16.042 grams. For every 1 mole of methane, my moles cancel because I have 1 in the numerator, 1 in the denominator. Right now I'm at joules per gram, but I need just joules so I can add these 2 heats together. And I know I've started with 5 grams of methane. All right, so my grams will cancel, and my delta H sub 2 will equal 2,556 joules of heat. Okay? All right, so I need to think about this. I am going from a gas to a liquid, so I am condensing. In order to go from a gas to a liquid, it needs to release heat. It appears right here that I am gaining heat or absorbing heat because this is a positive number, but I know that I am not doing that. I know that I am releasing heat, so this needs to be a negative number, so I'm going to put a negative in front of it. This is where we start to make mistakes. Please don't do that. We didn't check this up here. Let's go ahead and do that now. It says here in our cooling of our gas that it released 111 joules of heat. So if it released this much heat, we need to think about that. If it released it, the temperature should be cooling, and it went from 120 to 110, and it did cool. So this negative sign checks out. The positive sign over here did not, so we needed to add that. Okay, so the delta H for my entire cooling process here will simply be the delta H for step 1 plus the delta H for step 2. And the delta H for step 1 is a negative 111 joules, and the delta H for step 2 is a negative 2,556 joules. I have the same unit, so I can add them together, and that would end up being a negative 2,670 joules. Or if you put this in kilojoules, it would be a negative 2.67 kilojoules of heat that was released. Alright guys, I'd like for you to stop the video, pause it, and then work on this question. I expect you to have it done when you come to class. Just as a heads up, don't forget you need to sketch a diagram, a heating cooling curve. After that, you're going to want to label on your heating cooling curve each step. Make sure after you've calculated your delta H's that you ensure that they have the right sign by going back and checking, did the temperature change in the correct direction. If you're changing phases, in other words, you're doing a phase change, you're going from a solid to a liquid or a liquid to a solid, or a gas to a liquid or a liquid to a gas, you are going to have to assign that positive or negative of value to your delta H on that portion. Your delta H for all of this should be a negative 6,800 joules or negative 60.8 kilojoules. If you cannot get that answer or you did not get that answer, make sure you ask for help tomorrow in class.